Hello everyone, welcome to my talk. I'm Meng Xu from Georgia Tech, and today I'll be talking about fuzzing, and in particular, how do we use fuzzing to find data risk bugs in the Linux kernel file systems. So this work is our Krace paper, and it's a joint work with my lab mates Sanisha Kashyap, Hanqing Zhao, and our advisors Tesu Kim. So since this work is about data risks, so let's talk about it. What is it, and why we need a specialized fuzzer to find them? So in particular, the definition of data risk is actually super simple. It's basically defined as two memories trying to access us from different threads, such that the two memory accesses get to the same memory location, at least one of them is a write, and then they may interleave without any restrictions, like without locking or without ordering. So a classical data risk example is actually shown here. So suppose that we have a toy program, and then by using two threads, we try to increment the counter value. We want to get the job done faster, which is counting to 100,000. However, this is not actually the case in this program. In fact, any value between 50,000 to 100,000 is possible out of the programs. And this is because both threads are racing against each other to try to read and write to the variable counter. So of course, the more concurrent code you write, and then the more likely we're going to have mistakes in the code. And this is not very good news for the Linux kernel because the kernel is almost the most concurrent program we'll use every day. So here is a demonstration of the level of concurrency we would normally see in the kernel file systems. In the ButterFS file systems itself, it has 22 threads running in the background. And this doesn't even including the thread that is going to be forked out of these threads. And then these background threads are not just sitting there doing work alone. They actually interact with each other in processing operations on the file systems. And of course, with such a level of concurrency, there's every reason for us to believe that there will be data risks that may exist in the Linux kernel file systems. So here is actually one example that we find in the kernel file systems. And we say that if the execution flows like this, starting from thread 1 to thread 2 and back to thread 1 and 2, and then we see that the pointer p is assigned two values, where the first assignment is actually lost, which means that we're going to lose the control of the chunk of memory allocated by the kmalloc on the thread on the left. And this kind of data risk can be easily detected if we can drive the execution into this code path at runtime. But the difficult thing is, how do we even get the execution into this code path in the first place? Well, this is where fuzzing comes into picture. So basically, fuzzing is a way to explore the program states. And traditionally, we have been using the control flow graph as a way to approximate the number of all the states of the exploration in the program states. So basically, how it works with a control flow graph is like this. Well, starting from an input, we send it to the program, and then we monitor at runtime what are the edges in the control flow graph are hit. And then we summarize the effect in something called bitmap, which is highlighted here in the middle. So we after we run one seed, we're going to tweak something in the input. And then at this time, we expect to explore different sets of edges in the control flow graph. And then we again summarize the things in the bitmap. And then we do this on and on by keeping mutating the inputs until we find that, OK, after certain trials, there's no more coverage growth in the bitmap. And then at this time, maybe the most economical way for us to do is to shift the input some other things. And then by doing that, we're going to explore, again, different parts in the control flow graph, and then we can further expand our bitmap coverage. Well, this is actually how the conventional fuzzers, including the kernel fuzzers, has been working. If we're very lucky, the program crashed during the execution, then it's a clear sign that there is a memory error out of it. So this is how the conventional fuzzing process has been working. And this process has been very successful. The code coverage metric is actually behind all the modern kernel fuzzers, including the syscaller, the KFL, and their follow-ups. And this is also the key reason that over 200 memory errors are actually found and reported during the few past years. But if you're going back to our data risk example we find in the kernel, there are several issues that why the current fuzzing framework might face some difficulties in finding it. Well, there are two things. One obvious reason is that there's no crash in the data risk example. And basically, when the data is triggered, it might return some wrong error code to the user, but they're not going to crash the kernel. And as we see in the procedure, if you're not going to crash, we don't think that there's error here. So in order to bring the data risk explicitly out of the framework, we actually need a different set of checkers, which is called data risk checker, to even say that even if there's no crash, but if you observe the behavior like this, we're going to say there's a data risk. And due to time constraints, I'm not going into details on how we design data risk checker, but basically we check data risks according to its definition. So whether there are two memory accesses from different threads, and then one, if we have locks guarding between the read and write, we say this is not a data risk. And then on the other hand, if we can establish some causality relation, for example, something fork another thread and then fork another thread. If we have established this kind of relation, we also don't think this is a race. But other than that, we're going to say anything writing or reading to the same memory location is going to be a race against each other. So, but if this is the only reason why k-races are better than existing fuzzers, this is not going to be a very exciting project. So there are more fundamental things that drive the design of k-race. Again, going back to the data race example, but making it slightly more complicated in this case, is that right now, the pointer P is not a pointer anymore. It's actually an index access to the global array. And it's also easy to realize that if we can have x equal to y at the same time, we're going to bring back the old data race bug again. Basically, if x equal to y, then gx and gy pointing to the same thing. So let's check where x and y are defined, and then here we find the definition. And if we can further simplify the case, we get this. Out of the two threads working like this, can we have a case that x equal to y? And in this very simple case, we can simply enumerating all the possible interleavings, and then the answer is for sure. We do have two interleavings, giving you x equals y equal to 2 in this case. But the very interesting thing in this case is like all the interleavings are going to yield to the exact same code coverage. So which is shown on the left in the control flow graph. Whatever interleaving you take, we're going to hit exactly the same node and same edges in the control flow coverage. So basically, existing fuzzers measure the progress of fuzzing based on code coverage. And then this is a perfect example to show that this assumption might not be actually complete in terms of dealing with highly concurrent programs. So regardless of which interleaving it takes, the eventual code coverage is the same, which means, well, we lose some states in the program. And then putting them into a more visual term, it seems like, well, although we keep exploring the same control flow graph during different differences in thread interleavings, we might actually get different execution states in this case. Which means that we probably need a different view of fuzzing coverage in order to track the exploration in a concurrency dimension. And in order to do that, we basically turn into this sequential view of control flow graph into a two-dimensional view, where the control flow, the edges in the control flow graph is taking on one dimension, and also the interaction between these edges taking on the other. And there will be many interaction points between the two threads. And then these interactions can happen in all kinds of order. I mean, if thread 1 runs faster, then thread 1 is going to influence thread 2, and then the other way around. Therefore, the case we see in the previous example, we can have exactly two control flow coverage, but because their thread interleavings are different, their thread interactions are going to be different, we're going to hit into different program states. In this case, many executions will not be considered as interesting by the traditional fuzzer because they're trying to explore exactly the same edges in the control flow graph, but they will be considered differently in k-race because they're hitting different interactions between the two threads, and then by doing that, we will account for that they discover new states in the program, and then we need to reward them, and then probably treat them as a seed, and then further fuzz from there. That's how k-race adds on to the contribution of the fuzzings. So basically, by bringing the fuzzing to the concurrency dimension, we need to do two things. One is like we need to design the concurrency coverage, which exactly track how much progress we have been made in the concurrency dimension. And then the other part is like we need to have an interleaving generator, which not only trying to explore the code coverage, but now trying to further expand the coverage in the concurrency dimension. So going to the first question, how do we design a concurrency coverage tracking? So basically, like code coverage, we're going to design a bitmap where every dot in the bitmap here means that we find some meaningful interaction we haven't seen before. So how do we design such a bitmap? A strawman solution will be like this. Well, you have two threads, and then the next thing I'm going to do is say, while execution, I'm going to match the instruction in however we want. And then we can actually calculate a hash number based on how the instruction in the two threads match against each other. And then in this case, we're going to calculate a hash of the sequence of the instruction executed, and then we get some hash number. And then in the next execution, if we see we have a different ordering on the instructions, we're going to tweak the order there and then get another hash number. So this is how a strawman solution will look like, and it will definitely capture all the possible interleavings because this is on the instruction level. But there's a problem. For example, if you have two threads which have m and n instructions respectively, here is a formula that gives you the number of states. And to make sense, if m and n equals to 16, which means there are 16 instructions in the thread, you're going to have 600 million states, which, well, no one can actually explore in such a huge state space. It's too sensitive to thread behaviors. So even changing the order of instruction that doesn't have an impact on the thread execution is going to be counted as an interleaving, which is something we don't want. So how do we design a practical interleaving tracking between two threads. Well, here are some observations we can rely on to help to guide us on designing such a scheme. So one, only interleaved accesses to the shared memory matters. Well, for example, in a very extreme case, here there are two threads and they are not going to share anything. Their interleaving doesn't really matter at all because you can have the two threads running separately and it doesn't matter which part of the instruction gets faster or the other part gets slower. They're all going to lead to the exactly same output. Therefore, we don't need to track if they don't ever share memories. The second thing is like if you only have read and read accesses to the shared memory, which means like you never write to the shared memory, but only taking information from it. And again, it doesn't matter how they interleave because the shared memories, you're only taking information out of it and you're not changing it. The information you get is not going to change regarding to whether you get it first or second. Therefore, we don't care about read and read accesses. The only thing we need to care about is the write to read accesses, which means some thread defines something and then you try to read from the same location. So only this part of interleavings are meaningful interactions between two threads. And this is exactly what we are going to track in our queries. We only track the cross-thread write to read edges. And then this is exactly also the same thing you see in a graph before. So we see two threads are trying to interact with each other. We're actually saying that this thread is actually defining something the other thread is trying to use. So similar to the edge coverage, we use a bitmap to track how much you have explored in the concurrency dimension. So basically, if we see one write to read definition, we're going to mark 1 bit in the bitmap. And if we see write to read at different locations in the instructions, we're going to mark 2 bits in the bitmap. And during our experiment, we observed like there are around 64,000 unique cross-thread write-to-read edges, which means like a bitmap of size 128 bytes should be sufficient, which is way better than the 600 million bits in the bitmap. And then this bitmap size is roughly on par with what people have been using for AFL and then syscall. So then this is how do we design the coverage bitmap for the concurrency dimension. So the next thing is like we need to generate some inputs which try to explore different things in the concurrency coverage. Because by mutating the syscall arguments, there's no direct way of controlling how the threads are going to interleave on each other. So we need to actively manipulating the interleavings as well. So how do we do that? Well, the ideal case is like, let's permutate everything. Let's permutate each instruction in every thread. And then for doing that, we're guaranteed to enumerate everything we have in a bitmap. Well, that is certainly an ideal case, with the exception that, well, if you're going to enumerate all the interleavings among all the kernel threads, that is almost impossible. Because during our experiment, we observed that there are at max 60 threads running at the same time, which means that assuming each thread have only 10 instructions which access to some shared memories, that is, you're going to enumerate 10 to the power 60 possibilities, which again, no machine can actually do that within reasonable time. So what we do is instead of actively enumerating all the interleavings, we're starting with delay injections. So the idea is like, well, suppose right now all the read and writes are going to get the same memory location. And before we add in delay injections, the write at T3 is always defining the read at T1. And then the write at T2 always defining the read at T4. We have two bits marked in the bitmap. The next time we run the same seed, we're going to inject some delays before the read and writes there. And hopefully by injecting the delays, we're now going to distort the way that this read and writes are related. For example, previously we have T3 defining T1, but now T3 is defining T4. And then and also similarly, this time T2 is defining T1. So basically by injecting the delays here, we probe 2 bits out of the concurrency coverage. And then you can imagine that, well, as long as we can probe something more, we're going to add more delay schedule to it. And then we're going to hit more bits in the coverage bitmap. And then gradually we can fill this concurrency coverage. So this is how do we design an interleaving generator. And then bring the 3 components together. So the inputs to Krace, it becomes twofold. One is a syscall generated based on a grammar-based syscall generation like what syscaller and KFL is doing. And then we also have the interleaving generator, which every time is going to give you a new delay schedule. You have to delay at each shared memory accesses. And once we have this 2 input, we're going to send them to the program, and the program is going to execute. As long as we observe some improvements in one of the coverage bitmap, we're going to say this is a good seed, please keep it for more mutation. The feedback process goes on. And then for basically any fuzzers, we need to evaluate its coverage growth. For alias coverage, which measures the concurrency dimension, the trend is not too much different from branch coverage. It grows like exponentially in the beginning, but gradually it will saturate. But there are some interesting observations. It's like for systems which are much higher in the concurrency level, saturate much slower. For example, the ButterFS, which have I see like 22 background threads running at the same time. Saturated is much slower than ext4, which have like 3 to 4 threads running in the background. And also the alias and edge coverage goes almost at the in synchronization. For example, the blue one is the branch coverage, the red one is the alias coverage. They almost go in the same trend. But there will be time, for example, especially in the butterfly case, actually, there will be time that the edge coverage saturates much faster and the alias coverage is still growing, which means that if we are only using edge coverage as our feedback in the fuzzer, it means that we're going to miss those new states explored by the alias coverage tracking. Well, the same thing is not doesn't apply too much on the ext4 again because its concurrency level is not that high. And also very interesting, by enabling the alias coverage, we can also get a slightly more edge coverage than syscaller. And I think this may be due to the fact that we are giving each seed more time to see, like, if they make progress in the alias coverage, we're going to keep the seed a little bit longer. This same thing doesn't really happen in the syscaller. And that's why probably we get more branch coverages out of it. In general, we find 23 bugs in the in butterflies, ext4, and then also in the virtual file system layer. Not all bugs are actually confirmed by the developer, but at least 11 of them have been confirmed to be harmful, which can give you either losing the information or violating some environment, crashing the kernels, or some performance degradations. So in conclusion, like, fuzzing is really becoming a crowded topic now. And then Krace nicely fits in the scheme of how do we further expand the coverage metric to the fuzzing systems. And then certainly we can benefit from the developments in other areas too, such as how do we generate structured input, how do we do seed selection, can we extend this to other applications as well. So this will be very promising future works. And then in conclusion, so this is highlight I want you to take, shifting the coverage from a single dimension tracking, which is the control flow edge coverage, to a higher dimension, which including the control flow coverage as well as the interactions between threads. And with that, I conclude the talk. Thank you very much for listening.